We shall now invite Professor Fan Hong Jing and Associate Professor David Wilkowski to remain on stage to chair the morning session of the conference program. Professor Fan and Associate Professor Wilkowski, please.
Good morning, guests. My name is Fan Hong Jing from School of Physical Mathematical Science, NTU. To kick off the morning keynote, it is our honor to introduce Professor Konstantin Novoselov. Professor Novoselov was born in Russia in 1974. So he has been best known for his pioneering research in isolating graphene in the University of Manchester in 2004. He is also an expert in condensed matter physics, mesoscopy physics, as well as nanotechnology. And since 2014, he has been included in the list of the most highly cited researchers in the world. And in 2010, he was awarded the Nobel Prize in Physics for his great achievements, pioneering research in graphene and beyond. The title of his talk today is The Materials for the Future. May I invite Professor Novoselov on stage, please?
Good morning, everyone. It's really a great pleasure to be here. Frankly speaking, in the past couple of months, I've been coming to NTU, to my office, have increasing amount of collaborative research here. So, and I hope that I will keep this relation for the foreseeable future. And it's, of course, it's really a great pleasure to be here to celebrate this the 100 years of C.N. Yang. He's definitely although we are from slightly or a lot different fields, but physics is still physics, and in condensed matter, the field I am active in. So his contribution is, of course, also enormous. Even the gauge fields, which becomes increasingly useful as we switch to the topological description of materials, is fantastic achievements. And of course, he've got even larger legacy in condensed matter. Though I'm not sure if the word legacy is correct here, because of course every single scientist thinks that his or her achievements, the best achievements of their lives, are still ahead, and I'm sure is the case of C.N. Yang as well. So I'll talk today more about about my field, but I'll do some connections to the contributions of C.N. Yang as well, and of course. It's impossible to avoid graphene. You will see the reason why is it a very convenient point to start. But for those who are not familiar with this material, let me briefly introduce it. It's the thinnest possible material. It's only one atom thick. It's only carbon atoms arranged in a honeycomb lattice. In principle, supposed to be a very simple material, but yet it has a number of superlatives. Like is the most conductive, is the strongest, is the most flexible, impermeable, thermally conductive, and so on and so on and so on. And because of many of those properties, it's actually been earmarked for many future applications, from composites to optoelectronics, from energy to sensors, and so on and so on and so on. And that's, of course, so that's actually been quite the case, and already these days we can see many examples of graphene being used in our daily life. I mean, I'm quite positive that today you already touched graphene somewhere, And just to give you a few examples from 3 different sectors, like Ford, every single Ford car which you see on the road would have graphene under its bonnet, and it's mainly for in the composite plastics, and it's the functionality there is mainly for noise absorbing properties. Quite an unexpected, but from the hindsight, you would probably could guess that if you introduce 2D material, you have a lot of interfaces, and then you can scatter phonons efficiently. So from the hindsight, you could probably guess that this application would become very popular. Then thermal management. Graphene is the most thermally conductive material, and thermal management is one of the biggest challenge for modern electronics, and that's the reason why most of the devices produced by Huawei now use graphene for thermal conductivity and thermal radiation applications. And then if we go to the electronics and optoelectronics, so these days there are several companies which produce ultra-sensitive photodetectors for different ranges of the spectrum by combining quantum dots together with graphene, and then due to very high mobility of graphene, the effective integration time becomes very large, so you can actually gain a lot of gain very high sensitivity for pretty much any range of the spectrum, and the absorption here is controlled by the quantum dots. And then some time ago, because people have been doubting, so can we produce enough graphene? How easy is it in mass production? Because a long time ago, we started our journey with this material by using Scotch tape technique. You simply take graphite. Graphite is the material which you find in your lead pencils, and then you use Scotch tape and you exfoliate this lead material, and then the thinnest flakes which you get are the monolayer graphene. So then, and frankly speaking, the same method is still being used right now in our labs. It's very reliable, very simple, high quality devices can be gained from that. But then these days, of course, we require much more scalable methods, and depending on the price you want to pay and the quality you want to achieve, there are many other ways how to produce graphene, like liquid phase exfoliation, which is good for batteries, for composite materials, some bio applications, maybe flexible electronics, and then CVD method, which is the electronic grade graphene. These days we can produce square kilometers of this material, and then going into more niche epitaxial methods of how to make this material. But then still probably the main contribution and the main the most important thing about graphene, that it was the first two-dimensional crystal which was available to us. The first but not the last, because it really opened the floodgate for many other two-dimensional crystals, just crystals which are only 1 atom thick, to be discovered and studied. And the story goes like this: that if you can exfoliate graphene from lead pencils, what happens if you take other pencils, and can you get other two-dimensional crystals? So the answer is yes, and these days we're basically talking about the family of the two-dimensional materials, and this family now includes many dozens of different crystals, from the most insulating like boron nitride to semiconducting. So semiconductors can emit light, for example, to metallic, semi-metallic. There are superconductors and so on, and so on, and so on. So really many dozens of those two-dimensional crystals exist, and of course it's really exciting for us to study the properties of each individual crystals, because the moment you get into two-dimensional world from our three-dimensional world, the laws of physics change and you really get some new phenomena there. So, I mean, you can think that there are no knots in two dimensions, right? So the topological properties would be different, and so on and so on and so on. But then the fact that we have now this family of the two-dimensional crystals, and when I come to my lab, we have those 2D films, one atom thick layers just available to us readily. What we can start doing is to create artificial materials, which don't exist in nature, but we can create them by combining different layers, by stacking them one on top of each other, and then we create we can create any artificial material we want, and what is even better, that we can program its properties and program its functionalities, because we can control with the atomic precision the sequence of the layers. We can put some conductive layers, some insulating semiconductors, and so on. And so it actually works quite well, and we have many different devices now created through this method, like tunneling transistors, like photodetectors, solar cells. And for today's talk, I wanted to focus on a specific type of the two-dimensional materials, which was discovered probably just only a few years ago, but still became very, very popular. Is the two-dimensional ferromagnets. So it's the two-dimensional materials which have some ferromagnetic properties. And the reason why I chose this topic is because it actually resonates with one of the early papers from Yang, the spontaneous magnetization of a two-dimensional Ising model. I mean, Ising model is one of the most popular and widely used model for many types of interacting particles. It's very, very popular in ferromagnetism, and Yang gave an exact solution of this of the magnetization of the two-dimensional magnet, even though at his time there wasn't any two-dimensional magnets yet. So they were discovered just maybe 3-4 years ago. So he already created the exact solution for the Ising model. So luckily, why he was interested in it, and why is it interesting to us now? So generally, of course, in everyday life, we deal with the three-dimensional magnets, right? So the fridge magnets, the neodymium very strong magnets, they're all three-dimensional. And in 3 dimensions, I cannot say that the behavior of those ferromagnetic materials is boring. No, it's quite complex, but it's still not complex enough. So depending on the dimensionality of space, so we're talking about the 3-dimensional materials, and the dimensionality of spin, whether we allow it only to point up and down, that's 1-dimensional, or it can point in any direction in a plane, that's so-called XY magnetism. It's the 2-dimensional, or it can point anywhere in space, that's Heisenberg ferromagnetism. So in all those cases, we have a phase transition. So we know that this magnet can be magnetized, and at certain temperature then you cannot magnetize it anymore when the temperature exceeds the exchange, the interaction energy. If you go to the two-dimensional world, then the situation becomes much more complex and hence much more interesting. So Xie and Yang studied the two-dimensional model with the one-dimensional spin dimensionality. So spins can only point up or down. That's the so-called Ising model. And in that case, in two dimensions, same as in three dimensions, there is a phase transition. So you heat up your system, it stops being ferromagnetic. Now, for the other two cases, say for the spin dimensionality 2, there is only the so-called Kosterlitz-Thalles transition, which is not a phase transition. So you don't see the jump in a sense that you don't see a jump in the magnetization in the order parameter, but still you can see some order and some order excitations around the Kosterlitz-Thalles temperature. And in three dimensions, in three-dimensional spin, there are no phase transitions at all. So that's it just shows you that the moment you get to the dimensionality 2 one-atom thick crystals, their behavior becomes way more complex and way more interesting. And that's what we're doing. We're studying those two-dimensional magnets. So these days there are many of them, and really quite a variety, maybe several dozens as well. And so I'll just show you a few slides with the results on chromium bromide. It's quite a convenient it's quite a convenient material to study with the TC 37 Kelvin, so not too high, not too low, very convenient to work with. And so there are many ways how you can study two-dimensional ferromagnetism. Well, it's quite challenging to study ferromagnetism in two-dimensional materials, but people discovered several ways how to do it. So like magneto-optical Kerr effect, for example, if the magnetization is large enough, or tunneling phenomena. In our case, I'll just show you, in my lab we used many different methods. I'll just show you one method which is not so popular, but which in our lab we still utilize, is the whole magnetometry. And it's basically, the reason we do it is because it's still the reminiscent of my student years when together with my supervisor at the time, Andrei Gain, we used whole magnetometry to study superconductivity, mesoscopic superconductivity, individual fluxes going into those mesoscopic superconductors, or the motion of the domain walls in ferromagnets, so you can see the domain wall moving from one atomic plane to another. So the sensitivity of the method can be very high, and the idea here is that you basically take a whole sense. A whole sense is just a wide piece of metal where you send current, and then under magnetic field, this current, due to Lorentz force, start to bend, and it creates the whole voltage. Very, very simple method. But then it's non-invasive, and it can give you high resolution, but very high sensitivity as well, and it works in a very wide temperature range. And here, why we decided to study it again? Because it actually works fantastically well with those heterostructured materials which I showed you before, that we can create the whole sensor from graphene and then stack them together and then put our two-dimensional crystal again. So the whole stack becomes your complete measurement rig. So it's really, so you mix the materials and the devices together. So you just create this stack with the graphene Hall sensor, and then you bring your ferromagnetic material and you place it on top. Then you just send current and measure voltage. Very simple behavior, and that's the magnetization. So of this material. So if you go at low enough temperature, it starts to be ferromagnetic. So you see the usual hysteresis loop for the ferromagnets, and those individual steps which you see. It's basically the domain wall moving from one position to another, getting pinned and depinned, and then we can recalculate it into the magnetization. So then if you do it for many different temperatures, so you can just extract this magnetization, and you can extract the magnetic moment of your material, and that's exactly what Yang predicted in his paper, and we tried to do exactly that. So just on the picture on the right, so you see that at temperatures above 25, 22 Kelvin, there is no magnetization. It means that so you are above the critical temperature, and then below your magnetization start to go up, and so here so that's the picture from Xi and Yang paper, and you can see that it's actually fits somehow to our data, but not entirely, and that's what I was that's the phenomena which I was telling you before, that in two-dimensional crystals the situation becomes much more interesting. So spins are not purely spin up or down like in easy models. Of course, Xi and Yang assumed the easy model in his calculation, so that hence that's very sharp behavior. So in our case, in real materials, you have some more complex behavior, maybe something which was introduced fairly recently by Kitai. So we have some other behavior, and so that's why it's really exciting to compare our results with the exact predictions of the simple Ising model. So I want to move a little bit on here and talk because the title of my talk still materials for the future. So I wanted to touch base on the materials for the future. And so so here you can see one of the most complex materials which we created. It's really a combination of many different crystals, semiconductors, insulators, semi-metals there. So, and the idea of this crystal that you have semiconducting quantum wells where you can inject electron and Hall pair, and they can then recombine and emit light. And indeed, if we apply voltage, so then some light appears from those devices. And remember that we really create them by layer engineering. We put one layer of atom after another by hands, and it still works, which always surprises me. And then so we can create many of those two-dimensional. So many of those van der Waals heterostructures, we can tune them to emit at different ranges of electromagnetic spectrum. So because we have so many of those crystals, so here probably the most important is molybdenum ditelluride, because it emits right in the silicon range, so silicon photonic range. So you can combine it to be used for telecommunications. But then we can also grow alloys, and we can actually create many different, even more types of materials, and then we can actually really cover any spectrum and create any color of the LED, and that's something which we are quite busy with now. So now we're trying to create. We really do material engineering. So rather than sticking with one material which is given to us by nature, like I don't know, we always use silicon, or for electronics, or we always use steel for construction. So we really try to understand what is required for this or that application, and then we can create a new material really specifically for that application. And this is the new direction in material science, is the tailored materials with predetermined properties. The problem is that it's very difficult to relate the structure of the material and the property of the material. So usually we do it through trial and error. And for example, for this case, which I showed you, the emission of light, you really need to guess. So what kind of alloy do I need to put together to get into a particular wavelength? So in our case, we are trying to study. We create a huge database of different alloys and different add atoms in our crystals, and we use machine learning to predict their properties. So in this case, for example, we try to use those alloys for the catalytic properties, and we try to recreate the Vulcan plot, or so we can replace molybdenum with tungsten or sulfur with selenium. But the reason I started to talk about this material by design and AI for materials is because Yang, during his PhD years, when he was still in Tsinghua, still in Kunming, where Tsinghua was relocated during the war. So the year for this paper is 1944. So it's the final year before he moved to US. So he really created this very he's always very mathematical, right? So, and he created this generalization of the statistical theory of superlattices. And then when I was preparing for this talk and reading for this paper, I was actually very surprised to see that our methods, in our AI methods we use these days, are actually not that far away. So we didn't move that far from those original papers. So it was quite a pleasure to read it. So basically, we just create all possible defects, all possible alloys, and we create a special representation, introduce some quantum parts into it, and then we can actually predict the properties of the materials quite well with depending on the particular structure of the alloy. And I can tell you that those ideas from that papers are actually quite important these days for the creation of the proper representation for the AI. So it's just fairly new results. We just submitted a couple of weeks ago this paper. So I do have maybe 5 more minutes, or? Right.
Yes, you have even 5 minutes. Yeah.
So maybe I'll just so I told you that the current state of the art in material science, that we're trying to create materials with predetermined properties. So you tell us what you want, what kind of conductivity or what kind of color of the emission, and we try to create an artificial material with those properties, either through alloys or through the heterostructures. So there are many ways. How to do it. So is the current state of the art. It's not really in the industry yet, but we're trying to develop this technology. I still wanted to talk to you very briefly of what can we expect from the material science in the future, and sort of to introduce this. I wanted to show you two video clips. So some of you might recognize this clip. It's from the movie Terminator. So I don't know how many actually in the audience did see it. So the reason I'm showing you that the plot of the movie is that in 1991, so the movie was shot in 1991, and the plot is that a robot from 2029 was sent back to 1991 to kill Sarah Connor and whatever, so all those guys, and that's how we in 1999 thought our robots in 2029 would look like. So they would look like agile, be made of the liquid metal, flexible, self-repair, can change shape, and so be very practical. So now we are in 2022, and I guess you would agree with me that we're a little bit behind the track, and the biggest problem actually is not that we're behind. The biggest problem is that our general approach is completely wrong. So we would never get to those liquid metal robots if we keep with our current technology, and the reason is that generally our technology is the so-called top-down functionality. So can I ask you if there will be sound? Can you cue the sound? And so generally our individual components of our pieces are not functional at all. They only start to be functional when we put them into a system. Like individual transistors start to function when you put them into a multivibrator or a circuit. So those cogwheels start to be functional only when you assemble them together into the watch. And that's actually true not only for the watchmaking or for the robotics, or it's actually true for all our technologies, that the functionality comes only on the system level. If you look at the biological systems, they actually they work completely different way. They are functional on every single layer. Like proteins are functional in their own right, so they can change their conformation. They can do this and then change the conformation and do that, or biological membranes, or cell level, or organs level. So each have its own function or its own functionality. And this distribution of the functionality is exactly what gives us this versatility and adaptivity. And I would like to argue that that's exactly what we need to introduce into our technology to get into the next level. So what we want is that our materials, which we create for the future, are actually adaptive and functional in their own rights. And that's why we create this idea of the functional intelligent materials. So functional means that they can be programmed to do some certain functions, and intelligence that they actually have memory, so they can memorize and they can learn something. So that they can make decisions on their own way. Just let me give you a couple of examples. So one example is that we produce now smart membranes. So like graphene is quite good for membrane, for example, for water desalination. But then what happens if there is some toxic species in your water stream? What we do, we create a heterostructure, and we create those materials in such a way that if there is some toxic molecules, they change conformation, and then they can actually close those pores and stop water flow. So that's the example of the functional material. So another one is the work from my colleague Guy Bazin, who combines bacteria which emits electrons during their metabolite and conductive polymers, and then when this electron is emitted, it's collected by the conductive polymer, and that gets transmitted into your circuit. So you basically get a live fuel cell. But here the beauty is that those conductive polymer, they get polymerized as the bacteria grow. So it's a sort of a live bacteria. So the polymer helps bacteria to consume food and produce energy, and the multiplying bacteria help to grow, to polymerize this polymer from the monomer. So it's an active system by itself, and it just grows. It just grows on its own. You just give it sugar, and we're trying to do this kind of systems for many other applications as well. It's not easy, because the moment we start talking about systems with memory, it immediately means that we have some systems out of equilibrium, and physicists hate out of equilibrium problems. It's something we are not particularly used to, and not something we are good with. But we're still trying this, and the biggest challenge for us is really how close can we get to create living materials and to create life, basically, if you start with the non-living components. And we understand the basic principles of this work. You need to create a system, a composite system, with strong interactions, but also those interactions should be through different channels, because then you can create a degenerate energy landscape, and then you can direct your system through some phase transition to arrive at a certain point, and then maybe come back. And the situation is very, very similar to what you see in proteins. So proteins, why they're so versatile? Because there are multiple phase transitions, and they can change their conformation into in different manner. And the moment they change their conformation, new functionality appears, and then those energy landscapes. So you basically just navigate through it, and that's how your body functions. That's exactly what we're trying to do for our materials. And as I said, so it's quite so the paper of Xi and Yan actually helps not only to predict the properties of those composite materials, but also to predict the transitions which are very important. So I just before I finish, I'll just give you one example of such a material. So here we program the self-healing mechanism into our crystal. Is the high entropy alloy. So at high temperature where you grow it in a metastable state because it's stabilized by the huge entropy because we combine many different elements. But then at low temperature where you use it, if you make a hole, you have enough energy from the surrounding of this crystal, which helps to heal this hole and close it up, and basically just after a few minutes, so the crystal repair itself, so just like any life system. So we're basically redirecting the entropy into the enthalpy depending on the external conditions. And I would like to stop here probably, and just I hope you saw the logic that so these days we are good at producing materials on demand with the predetermined properties, but in the future we actually want predetermined functionality. So we want active materials which would be used for many different applications. And again, it's really a great pleasure and a great honor for me to talk at this meeting in honor of Xian Yan. Thank you so much. Thank you.
Thank you very much, Professor Novoselov, for very inspiring insight to the material for the future. Now we have a question-answer session. You may scan the QR code to send your questions, or just raise your hand. So Asha will send the mic to you. We want to start the first physical question. Or may start the question from online first. Most of the audience actually is online. Okay. The first question I read for you is that how would your research help spur the development of more sophisticated objects, such as 6G broadband networks and autonomous area ride-hailing services, and advanced engineering feats such as world-first semi-toppled skyscrapers and buildings that adjust its functional automatically? It's quite a complicated question.
Okay, so it's a really very complex questions to a simple physicist, right? To a humble physicist. But so first, I mean, there are many possible applications, and frankly, I'm not sure I've got answer to all of them. So we're just starting, and we have only limited results yet. But so something we are focusing on are like active membranes. So we really can program. So these days we can program our membranes that they can be sensitive to different stimuli. Say you have sunlight or rain, which is slightly acidic. So you can think about a rooftop which can desalinate water, so just clean water by its own, and getting energy from sun to convert the absorbed poisonous species and to degrade it and put the clean water through. So it just I'm now thinking out loud based on what kind of things that we've got already. So we have the enhanced catalytic activities in our membranes, or controllable water permeation, controllable adsorption of certain species, and so on. So in the electronics, so you can any material with memory would actually create so-called memristas, which are useful for for neural networks, basically simulating real neurons. And that's really one of the biggest challenge now, because of course everyone seems like using a lot of AI these days, some for good, some for bad. But what people don't realize that those AIs are still based on the real transistors, and the amount of energy we consume in those AIs, in those neural networks, in the GPUs and TPUs is really massive. So that technology is very hard to squeeze into your mobile phone. So we really need some new solutions for that based on materials with memory. That's another application which we envisage.
Thank you very much for the answering. There's another question. People are very interested about the broad future of the materials. So the last question, last year there was a paper using pulse voltage to produce graphene. How do you think about it? Would it make mass production of graphene become possible?
Frankly speaking, it's mass production is not really, I mean, I know the paper, and mass production now is not a big challenge at all. And so, as I said, these days, depending on the particular form of graphene, because there is one generic form named graphene, but it doesn't tell you much. Like there is a generic name of plastics, but there are so many different plastics, and then for one type of application you use one plastic, for another you use a completely different plastic. So same with graphene. For example, they use hundreds of tons, maybe thousands of tons of graphene every year for lithium batteries. So it's an important component for lithium batteries. For the electronic applications, you would use a different type of graphene. So the biggest challenge is not different methods how to produce graphene, but how to adapt a particular method to and build it into the technological chain, that you need to reduce the temperature of the production to match the silicon technology requirement, or you need to increase the size of the crystallites. So that's the biggest challenge at the moment, and that's what many engineers in the world are busy with now.
Thank you very much. Actually, there's a lot of questions online about the future application potential for 2D materials in our future life. But because of time, we're not able to address all the questions. Please join me to thank Professor Novoselov again. Thank you very much for your talk.
Thank you.
And now we're going to have a coffee break. Guess you may proceed to the foyer for some light refreshments. Please be back and seated at 10:50. Okay, we're going to have a half an hour break. Thank you very much.